by the TV. The slight agenda is just kind of mingling and food for a few more minutes, and then we'll get started. For those who don't know, I'm Tim Arif. I will be the one doing the presentation of Spark and Databricks, and this is like the second meeting of the revived Azure Chicago Loop Meetup group. Chicago Loop Azure Meetup. Chicago Loop Azure Meetup.
Or Chicagoland, or
say a clam.
Welcome aboard. Yeah, we love our nautical theme jokes. Apparently.
Yeah. Hi, welcome.
Hi.
Have a seat wherever. I'm gonna grab some more chairs.
It's really hot in here.
Hey, Tim.
Yeah.
Can you do me a huge annoying favor?
Probably not.
Okay, cool. Can you take a picture before they get upset with you?
Before they what?
Before they get upset with you for the presentation.
You want a picture of him?
Yeah, I just want a picture of Tim with the group. Because we didn't do that last time, so we don't have any proof.
I don't like pictures of me. Yes. Okay, so you want the whole group to...
They don't have to look at the camera.
I think if you go out there, take a picture, get some.
That'd be great. Thank you, Larry, for jumping in.
You're welcome.
Pictures.
Act like you're doing something, Tim.
Everybody looking.
I'll point to my clam.
Thank you.
The wise choice.
Yeah, good.
I think she's done.
Thank you.
We'll wait for him to get his plate and then we'll start. Or both of them. And then we'll start.
Did you explain the restroom to them?
I did not. Okay, so if anybody needs to go to the bathroom, go out near the elevators. Looking at the elevators, men's will be on the right. It's 3, bunch 2s. If you're a female, it'll be on the left. It's 3, 1.
3, 2, 1. It's all up there. So
Yeah.
3, 2, 1, and I think there's like 3 1s.
3, 1.
4
But
1s,
just
5
keep
1s.
pressing it until it turns green. But yeah, so you just kind of come in or go out the same way you came in, and it's on the wall. So.
Yeah.
Good thing they made it separate. They go separate. So one.
Yeah, I could.
I was actually surprised they did that for simplicity. I would presume they would do 3 2s for everything.
Oh no. Over here. No.
Good.
Here you go.
So today we'll be talking about Azure Databricks and Spark, mainly Spark with a little bit of Databricks at the end because it's more of how you interface with Spark. Who's all actually used Spark and or Databricks here? Well, so like nobody, so I can pretty much lie to everybody and y'all think it's true. So I'm Tim Arif. Here's a beautiful wedding photo of myself from like 2 weeks ago. I'm a data architect at 10th magnitude. I help deploy, deliver, architect, and design any kind of data solution we have. Usually, I'm obsessed with Spark right now, so I usually try and jam that down everybody's throat. Sometimes it works, sometimes it doesn't. So a few of the parts of the agenda, we're reviewing Moore's Law, what it is, why anybody should even give a crap about it. Introduction, just like what Spark is, the architecture of it, and Databricks. So Moore's Law, why do you care? Like, Moore's Law essentially was a paper written by Moore, who was, I believe, he's now president of IBM or something. He was a professor back in the day who wrote essentially all microcomputers would be doubling in speed and power year after year after year. Moore's Law is over, as you can tell, you're going from i8 4.7 to i9 4.8, barely getting any cores. We're not doubling. So as it happened, though, companies started buying more and more hard drives and storing more and more data. So now we went from megabytes, gigabytes, terabytes, petabytes, and Yottabytes? Yeah, something like that. I know at the Spark conference, they actually had people demoing what it's like churning through that kind of data with Spark. So with that, what does that mean? Well, now that we can't scale large, we're going to scale horizontally. So languages like Spark and highly distributed computing will come into a lot bigger play, because we will go basically link up as many machines as we need to get the job done now and churn through the data. So Spark originated at UC Berkeley. It was founded because people are having the issue where one machine couldn't handle what they were trying to do, so they just decided to try and coordinate multiple machines together. And it's had a pretty short life, but it's gained a lot of speed and momentum, especially in the recent years. With the release of Spark 2.0 and going forward, it went from being a little more complicated to simple and straightforward and faster. And it comes from an academic background, so they try and open source everything they do. So Databricks, who has some of the creators of Spark, actually open sourced Delta Lake a week ago, basically where you can help layer Delta Lake on top of your blob storages or data lakes to essentially allow it to interact like a relational database. So we went from relational to NoSQL and now back to a relational. Everything seems to come full circle. So what is Spark? Spark is a distributed processing engine, meaning it'll go horizontal and you can link up as many computers and cores and executors as you need. It is an extension of MapReduce, so it's like Hadoop, but 100 times faster. It is a general purpose framework for cluster computing, more of the distributed aspect. And like I said, it's way faster than Hadoop. If anybody's going to implement Hadoop anytime soon, don't, and just use Spark. So Spark is like a unifying engine. It is, the quote from the book is a unified processing engine that can analyze big data using SQL, machine learning, graph processing, or real-time stream analysis. Spark is built up in layers where everything's on top of a Spark core with low and high level APIs. So you can see like a rough estimate of these. So the RDDs, why am I still popping up? So you have the RDDs, data frames, structured streaming, and you can link it up with any amount of data sources, and you have an abundance of environments for how you can run Spark. You can run it locally on the computer, you can run it in Kubernetes, Mesos, Databricks, pretty much anywhere you can install stuff, you can run it now. Granted, it's going to run terribly on your computer, so it's good for unit testing, but that's about it. The Spark architecture. So the couple of key points is everything runs through a cluster manager. So you essentially need something that can tell your workers what to do. So meaning, how do you actually get this to scale horizontally? You need one lead node that essentially tells all the other smaller ones exactly what to do and how to do it. So the way it does that is with a cluster manager, which is like a standalone Spark where you run it locally. Yarn, Mesos, Kubernetes can do it, but I think actually Kubernetes just got adoption in 2.4, and in 3.0 they will have full adoption for fully supported Kubernetes support, fully supported supports in a sentence. And then, as everything works, you have your driver, which will be like your Spark context, which comes from your code. So as you write, it essentially acts as a driver node, which pushes to a cluster, and the cluster will send that out to as many worker nodes as needed based on however many partitions you set up, which we'll be learning about. Spark language APIs. You will see a couple new ones, mainly .NET on here now, because that's extremely recent where you can actually use .NET with Spark. But the standards are, so it's built on top of a JVM. So the standard languages you can use are Scala, Java, and then SQL, Python, and R. Everything, the way all the languages work is it all routes right back through the Spark core through the the JVM, and processes in the same exact way now.
Is it .NET F# or how?
I actually have no idea. It was just announced like 2 weeks ago that they are building a library to allow you to do .NET.
Yeah, it's weird. It's got a JVM bridge. It's kind of funky. I was playing around with it.
It's still super new, but
Yeah.
they are definitely, there are a team of people at, I think, Databricks actually, who are attempting to make this full-fledged so any language can interact with Spark. Because right now, like, you're isolating a lot of Azure people and Microsoft Stack people, because who wants to learn Python when you can do C# really well? So the Spark session interactions, which I've already alluded to a few times with the JVM, basically you have your Python or R process or any language out there. It'll go into your JVM as a Spark session. It all breaks down into the same exact RDD frames, the resilient distributed data sets, and then that will pass over to your executors. And then all the work will get done, and it'll return your responses. There are like a multitude of different styles of APIs. They're mainly known between like the low level and high level. So RDDs are your lowest level API, where they were the initial thing created with Spark. It's usually what everything will end up turning into anyways in the JVM, even outside of your knowledge, it will happen. You can have distributed variables, and then the higher levels, which is usually what people should be using nowadays because of how much faster they are and easier to interact with, are your data sets, data frames, and SQL. So the way it's stacked in the picture is like you have like basically a pyramid. The higher up you get, the further away you get from the way it was originally programmed and the way it works inside the JVM. But it's still all interacting the same way because it's all based on a set of APIs that feed it and transform it all into the Scala code on the back end to run on your JVM. So what languages should you use? Scala or Python? Even nowadays, you really may not even want to do Scala because you can do like special things in Python that can run just as fast as any kind of benefit you would get from Scala. If you really are a diehard Java fan, you can do it. It'll be just as quick, but I've met very few diehard Java fans, and everybody seems to have at least 1 or 2 people on their team that can do Python. So I always recommend Python because it's the quickest and easiest to pick up and start running with. As you can tell, even from the RDD difference, the one that's aggregating 10 million int pairs, you can tell how many seconds it takes just from the same. So before, everybody would recommend Scala when there was no data frame API. The Scala was about twice as fast, like 2.25. Now that there's the data frame API that came out in Spark 2.0, they're just as fast. So you don't need to write Scala anymore. You don't have to worry about learning the functional. You just need to make sure to write your Python in a functional manner so you don't accidentally overloop your system and basically drag everything back to one machine rather than letting it stay horizontally spread out. So some of the terminology you'll need to know is like, what is a data frame? Data frames are essentially, imagine an Excel table or a SQL table in memory for what you're programming. It's the most commonly used structured API, especially now that's getting more and more support as the versioning goes up with 2.4 and 2.5 and 3.0. The partitions are how your chunks of data reside within the many Spark machines. So if you set up a partition based off a state with 50 different states, you could spin up a cluster of computers with 50 cores that can then each have a state per core, and that would be it. So everything would only compute what is on that one specific core for that one specific state, which is why Spark is so fast and like starting to become the leader for big data technologies. The transformations. So normally, if you're on one of your other programming languages and you tell it to do something, it does it instantly. Not in Spark. Spark likes to do everything very lazily, which is lazy evaluations. So the transformations stay abstract until it can actually have something to react on. So when you start programming in stuff and not actually committing an action, you're building out a DAG graph, which is a directed acyclic graph. Basically a list of instructions for what it will do once it actually receives an action. So that is referred to as like lazy evaluations, where Spark will literally wait till the last moment to do anything possible so it can create the most optimal processing power for you. So it tries to take care of a lot of the work with optimizations. Granted, you still will need to know how to do some optimizations to avoid some huge pitfalls. But with the lazy evaluations, it tries to take care of it as best as it can. Actions are what trigger your transformations and cause everything to start running. An action will cause your DAG to work and activate. There's 3 types of actions. There's actions to view your data in the console. So you want to view your data frame, see your data, return your integer result of like 2 + 2 or whatever. As soon as you do something like that, it forces it to come back. Example, like, so like if you do 2 + 2, it'll cause it. But if you tried filtering out something, that's a transformation. That won't happen until you actually did your 2 + 2. The other actions are like anytime you try and collect data in their native objects. So if you're going from Spark to a pandas data frame for some reason, that's going to cause an action because you're now going from Spark to a Python language, so it'll pull it all back. And then anytime there's an output, so when you're writing out to your database, writing out to your data lake, blobs, Kafka, Event Hub, whatever, that causes an action, forces your DAG to run. Actually, are there any questions currently? So with transformations, there's narrow and wide. Narrow transformations are when you only need your data to stay on one machine. So one core can do your transformation accurately. So if you said add 1 to everything, that would be an example of a narrow transformation, and it'll all stay on your one machine. Anytime you start getting really complex with filtering, large equations, algorithms, you're going to do wide transformations, and it's going to shuffle it. So when a wide transformation happens, you see a ton of arrows, lines of what's going on. It's shuffling data amongst all the different executors, so that way everything can run as optimal as possible. So sometimes your partitioning may not be as good as it could be, where you would have a 1 gig file on each core. You may end up with 2 gigs on one and a half a gig on the other. A shuffle partition would force those to re-even out as best as possible. The default number is 200, which is kind of key to know, because usually whenever you're doing any kind of testing, you're not going to have a 200 core machine to play with. You usually won't see those until you have like production loads in your test. So that's when you get to really do your optimizations, actually force different partition levels and how many shuffle partitions you have happen.
Is this something that happens automatically, or you actually have to plan for this?
Both. So you can have it happen automatically as part of the DAG. So that's why it does the lazy evaluations, where it'll wait until the last second to actually do any of this kind of stuff. So it'll find the most optimal pattern inside of how it'll run and then do that. There are times, though, where you will want to force this to happen, which like anytime you have, you usually want to stay under 200 megabytes per core. Anytime you go above that, your core's gonna like run slower. So you can force shuffle partitions and partitioning to happen early to make sure you stay at under 200 megs a core. So the optimal partition calculation. So your default's 200. Most of the time, you will want to use non-defaults as soon as you're getting to any kind of data sets that are large or you have a huge cluster. So when your partition count, so the key equation, if anybody remembers anything from my talk today, partition count equals your stage input data divided by your target size. Your target size should be 200 megabytes. Databricks, other companies will tell you it's 250. You talk to any of their solution architects or any people who've actually worked with Spark for a while, it will all tell you it's 200. It runs way faster, smoother, and better. So that's the only equation you need to do. Stage input divided by target size, and that's how many shuffle partitions you can force on it. So, quick scenario just so we can reinforce everything. You have 100 cores, 150 shuffle partitions, and you have 500 megabytes per partition. So that's a total of 75 gigs. How do you optimize this? Attempt 1. We can decrease to 100 shuffle partitions, which will give us 750 megabytes average, and it'll reduce the number of tasks it runs to 1 per core. So once it runs once, it means it'll be done running. Try 2. We can increase this to 200 shuffle partitions, reducing our size of per core to 375 megs, but then we run 2 tasks per core. So essentially the job's run twice. Attempt 3, we can increase the number of cores to 300, giving us an average partition of 250, allowing the job to just run once. Or we can increase the cores to 375, average partition of 200, reducing the cores to 1. Ideally, you would try to do attempt number 4, because you would get the ideal core size for everything, data size. However, 375 cores is a lot. If you're on a client or you're working with somebody who your job allows you to do that, have at it. Your stuff will run crazy fast and everybody will love you for it. So anytime you're playing with large data, you just need to remember target size divided by the total size divided by target size is the partition size you want. That will allow anything you do to run extremely fast, even if you write it poorly or cause loops. And I was supposed to ask you guys, but I did not. So why would you actually use Spark now? So now you've learned some of the cool things on it. Well, you can use it to do anything. You can do ETL, data, machine learning, streaming. You can use any of the common languages you want, as we've learned. There's data frames, there's tables, there's cluster managers. They can then output everything to databases or connected BI tools. It covers all elements of big data. It covers all the buzzwords. You got your AI, machine learning, and it's all in one language, one workspace. You have your data scientists and your data engineers actually working together for a change instead of being siloed and never talking to each other and just yelling about why the APIs aren't correct. So the biggest common use cases are large complex ETL, SQL analytics, streaming, machine learning. So anytime I'm saying large complex ETL, ideally you'll be in the terabytes at least. Yeah, you can use it for smaller projects more as a learning perspective than anything. But if you're using Spark in production for 10 gigs, 8 gigs, 12 gigs, you should be ideally, your course should run for less than a minute, if that. And hopefully you learned a lot from it because you won't overkill with it. But as this language is coming up and learning, I always recommend everybody, if you can get to do it, do it. It's the best time to learn when you have small data where you can actually fix and play with everything rather than attempting to optimize 5 petabytes that keep spilling off your disk and crashing your cores. Because as you're learning, you would have no idea what is happening. So what is Azure Databricks? Databricks is a unified analytics platform that helps even bring everything together even more than Spark itself. So now you have the nice notebook feel that data scientists love and every other software engineer hates. But you can still run everything on the same core. You can connect up your IDEs, you can link up everything you want to that Databricks core and deploy it out. And you can also have all your data scientists working in their notebooks. You can have data engineers in there too. Everything's shared. You can create custom tables and just split everything inside of the Databricks platform. You can run Delta, MLflow, Works, Tensor, literally pretty much anything you can think of nowadays. Databricks is trying to adopt in there to make everybody's life easier while developing. So like an example of how Databricks would actually fit into your workflow would be Lambda architecture style, which is what this is. So the Lambda is meaning you're doing streaming and batch loading at the same time. So at the top, we have streaming data with event hubs that Databricks can harness. At the bottom, we have Data Factory doing batch loads to Data Lake, which Databricks can pull in with Spark. Well, once everything's in Spark, Spark doesn't care if it's from streaming or batch. You can pretty much do everything to it as you could before, with a couple caveats with streaming data. If you want streaming to actually work with your batch data, you need to exit the stream. Excuse me. You can do that in a couple ways. You can do it with in Databricks, you would do it with Databricks Delta. You can drop the data off, streaming into a table. Even though the table's never-ending table and will always get new data, you can still query the table and treat it just like a batch load and then move on. You can do a for each loop to break the streaming loop to output RDDs once they reach a certain count, or a time limit. So like every 10 minutes, drop the stream into a new data frame. Every time you hit 10,000 rows, drop the stream into a data frame, and it'll keep doing that unlimited. So as you get to Databricks, you can then pretty much connect everything you want to. You can get your data warehouse hooked up. You can export data to it. You can import data from it. You can go to Cosmos. You can do all your machine learning stuff with Kubernetes machine learning, or you can do it all in Databricks. Like it basically is set up to connect to anything of everything you would ever want. Something like this would be for a very large enterprise customer. Usually if you're doing it yourself, you would whittle it down a little bit. You wouldn't need SQL Data Warehouse or Cosmos. Those are both really expensive. You can throw in just a normal SQL server, or you can go directly Spark to Power BI or Tableau, wherever your front end is. Databricks has a wonderful CI/CD pipeline with a beautiful REST API that takes care of all of your work for you. This little tiny Python class will take care of all of your deployments for Databricks notebooks and dropping them off. All you need to do is pass in a few variables, and it works. Yeah, it will pop in directly in a notebook right into your Databricks environment. So now that that's happened, let's look at some actual code that I've been lecturing. Now that I've been lecturing about everything for a while. So you can easily read from blob. This right here loads up a table in Spark for me. What is it, 11 lines of code? Is now doing batch loads. It's inferring so you can define your schemas in Spark, you cannot. I chose not to because it's a batch. Anytime you're doing a batch load, you don't need to. You can tell it to just figure out my schema for me. I don't feel like writing this stuff out. If you're doing streaming, you have to write it out because it's a never-ending data frame. So it never actually has time to analyze what's in your data to create your schema. So here I'm basically just saying, read this from this blob storage at the top. It has a header, and here's the location. Now go make a table called Pokemon for me. And the reason it's Pokemon is because I will be doing a demo, and I grabbed one of the only clean Kaggle data sets, which was Pokemon. So once it's there, once that's done, you can then just load everything directly to JDBC or any kind of output of a database you want with basically no code. Pass in your variables, create your JDBC URLs, and now you're writing into your database. It could be Postgres, SQL Server, Redis, whatever. If it can take a JDBC, it can write to it. So a real world example of how you would create a streaming example would be this giant mess of code that makes no sense to anybody. Basically, if you look at anything above the top from Hadoop configuration up, from Spark session up, Databricks takes care of all of that. So this code was deployed on Kubernetes. So we had to basically start up like the Spark service and basically identify everything Spark would be doing with where it's grabbing code from and data. And at the bottom, it's basically just taking JSONs from Blob and streaming them real time into a Kafka server. And here's what it would look like to then read it and go to JDBC. Notice the huge data line coding differences between Databricks and running something on Kubernetes. You're up and running a lot quicker. Like you don't have to pay somebody to sit there running Kubernetes. You basically are just, all right, Databricks, turn on, start my cluster, good to go. So I'm gonna do a quick demo. And because I forgot to start my cluster, we're gonna have to wait a few minutes. And if I can use my Mac. I'm a PC person, so don't yell at me too much. So let's go to clusters. So basically, the Databricks clusters will turn off if you're not using them. You can set them up to turn off at any intervals. I mind, because this is my personal account, clusters will drain your bank accounts if you leave them on, by the way. Like I've seen overages of like $40,000 for people. Turn them off. If you're running a streaming service in Databricks, end the stream because it will not turn off if your stream is running unless you manually kill it. So while this is turning on, I'll walk everybody through how we can quickly create a cluster. So in Databricks, so in Kubernetes or anything, you basically be having to, actually I don't even know how you set up Kubernetes. It's a pain and requires effort. In Spark, in Databricks, you click new cluster, plan demo, and yeah, DS3 to be about what? 55 cents per DBU, that's not bad. All right, that cluster's now creating. I have no infrastructure work to do. That's just gonna create, and then I can just link up my notebooks to that cluster once it's on. That's it. Databricks is just a wonderful product for just getting up and running quickly. If you want to show off some cool POCs, get your stakeholders or your bosses intrigued quickly, or you're just learning yourself, you can just spin up a Databricks. They have community editions, so you can turn on a community edition, and they'll pay for all of your compute and just let you learn everything. Let's see where the clusters are at. Yeah, so I guess while we're waiting, I can explain a little more. So you have your interactive clusters, which are the clusters you're actively, essentially doing your dev test on. So if you're developing, you're on an interactive cluster, and when you're actually scheduling production level workloads, you'll be creating job clusters that you'll assign to those. So that way you can make sure, accidentally let some new person scale up a 200 node compute cluster and cause you have a $50,000 bill without knowing it. The job clusters, as soon as they run, spin up, they delete themselves and go away. So as soon as they're done, they're gone. You don't have to worry about the pricing. I don't care about that cluster. We are still waiting. Sometimes, so the clusters in Azure will go anywhere from, well, I guess while this is loading, anybody have any questions at all?
Is this a separate portal? I see your URL. It's like
Yeah, so you still go, so you spin up your Databricks environment inside of Azure, if you're using Azure, and then when you click into the service,
bumps you over to a different.
Yeah, so basically it'll bunch you into a new workspace and force you to re-authenticate with AD.
Okay.
So AD authentication is built into Databricks, Azure Databricks that is. If you're in AWS, or I don't think it's in Google yet, you have to essentially set up your own authentication system. So it's kind of nice that Azure takes care of it. The difference between AWS Databricks and Azure Databricks is Azure Databricks is Microsoft's Databricks. So they have some sort of whatever deal worked out to where Microsoft, as with most things in Azure, controls it. For AWS, Databricks can do whatever they want to. Amazon pretty much has no say, from what I've learned. Let's see where we're at with the clusters.
We've got a couple minutes. It might be a good time for a quick break. People want to
Eat
Yeah.
more.
go to the restroom, eat more.
Hey, Tim,
Yeah.
you mentioned that there's a good place to get that there's a community edition available. Is that through the Azure store, or how do you get access to that to go in and play around?
I believe you just type in Databricks community, and that will pull you over to Databricks' website, because they'll be the ones hosting it for you.
Okay.
And you just ask them for an account, and you'll be hooked up with a small couple gig one.
Cool.
Basically instantly.
But that would be different from the Azure one.
Yeah, but yes, but that would be more of the authentication and how you do it. Once you're in Databricks, it all runs the same.
Okay.
So this is a great learning environment. Let's see.
Are there any courses that you recommend for a beginner?
There are through Microsoft. I can go through and do links afterwards.
Okay.
Is the cluster actually turned on now?
Yeah.
So some of the code I showed everybody earlier about pulling from Blob is actually code we're using now. I just didn't feel like setting up a key vault and doing secrets and everything. So I put it into a different notebook, and I'm using the Databricks API to force that notebook to run. So just by running this one command, I am now calling out to a completely different notebook. Nobody can see. It's going to run, and it's going to create a temp table for me based off of the Pokemon data set from my Azure Blob that I took off of Kaggle. And just like Jupyter, it's basically just segmented type space where anybody can write whatever they want. One of the cool things while this is doing it is you can type in any language you want inside of Databricks. So all those APIs. So right now my notebook's set up by Python by default, but I can just type Scala, and then it'll start recognizing the fact that I'm typing in Scala now.
Nice.
Same with SQL. All right, so what we're gonna do here is I'm gonna take, so now I've created that notebook, create a global temp table. If anybody knows anything about databases or anything, you can do that in databases. It's usually looked down upon very poorly. Spark does not care. Have at it. You're not using your disk space. You're not using your compute. Databricks, Spark, go for it. So basically, we'll just need to call in some PySpark stuff because we need to import all the functions and types. So now I'm going to basically set up a Spark configuration to pull the global temp databases from Databricks and then build out a Spark table to then query. So now that I queried it, that ran in 0.06 seconds, pulled in the data, and it's even showing me my schema now, what I'm reading. So I don't actually have to show or display any of this unless I want to, because I know what the schema is, I can just open it up. So now, because I want to show off some of the SQL APIs, I'm creating a temporary view of Pokemon in the SQL syntax. So right here, we're displaying Pokemon via the data frames API, which is what we're using right now. So anytime you run Spark, because it's calling an action, you can see the stages it ran.
How large is this database?
It is minuscule. It's 500 lines, it's like less than a meg.
Oh.
I actually have, I do a reduce method later to grow it up a little bit larger so I can show a difference between a couple different UDFs. Basically, you can, and this is the DAG visuals I was talking about, because this is a small workload, it's a tiny DAG. Let's see, click that. And then as you're doing this, you can interactively change the way you're viewing everything, and it doesn't affect your data sets at all. You can even change the way you're plotting. So right now, it's set up to plot your Pokemon types based off their attack. Essentially, what Pokemon type is the strongest person will have the highest bar, and I'm just grabbing the max. So whatever Pokemon is the strongest for that type is what we're seeing. If we want to run this in the SQL API, because we created the Pokemon table there, we just type in the % SQL at the top, and then you just start typing in ANSI SQL like it's nothing. If you know ANSI SQL, you can interact with all the SQL Spark API pretty much fluidly. There will be occasionally a couple nuances. I've actually encountered them a lot, and I always forget what they are, and basically just go, oh yeah, I forgot you can't do that anymore. That's one of the APIs I wouldn't, like, if you know SQL, I wouldn't worry at all about learning it. You know that API if you know SQL. So now what we're gonna do is we're gonna reduce the data frame, which essentially is adding a multiplicative value to it. So we're gonna create a larger data frame here. Basically, as you do things, you can create any kind of methods that you want, and then force those methods to, you can then enact those methods onto your data frames. So what I'm doing here is I'm running a union all method, function, where I'm just multiplying it by the data frame. So I can take unlimited amount of arguments, and then it will union all those data frames together. So then I just ran Pokemon a bunch of times. So it's basically like union all Pokemon, however many times that is, and then I'm running a count on it just to show that it's gotten larger. So now that it's ran, we have 9,600 rows, and we can check out the stages it's done. So now we can tell that it's actually did a lot more here. So basically what it did was it grabbed every single data frame as a different one of the boxes, and it just starts unioning them together. So as you get more complicated with the Spark and what you're doing, your DAGs are going to get way more complex, which is when you have to start really paying attention to your shuffle partitions and making sure everything's only happening once. So from there, we're going to walk through UDFs. So if people have ever used pandas, you know what a UDF is already. They're essentially just ways you can manipulate your data frame with a function. So if you wanted to force it, like, so with this one, I'm going to force everything to become uppercase, and I'm going to create a new column in my data frame. So you just literally just set up your function, and then you just register your UDF to Spark, what it's going to do, and what it's returning. Once it's done, you can run it against your data frame, and then I'm going to display the data frame right after. So I'm calling the big data frame, which is the 9,600 row 1. I'm making a new column with column upper, and now I'm running the data frame against the names of the Pokemon. So now you can see the results where everything's just capital. This ran in what, 5.87 seconds? Bez, let's see if we can. So when if you run a normal UDF inside of Spark, it's going to run everything on one machine, one core. UDFs by nature in Python are not set to scale horizontally. They do not interact with the Spark's core system, so they will all go to one machine and wait for it to compute. Which is why I started trying to grow this data set, because Pandas UDFs is a special vectorized UDFs created by Databricks that it's open source. You can pull into normal Spark, you can pull into Kubernetes or wherever you're running it, and run a vectorized version of your UDF, so it'll run more efficiently and actually split against all the cores. And basically you just run it as defined as pandas UDF type scalar, so it'll scale correctly. And then that'll use Apache Arrow, which helps it horizontally scale out across your machines. And it's doing the same thing, just creating everything to uppercase. So if we run that, it's probably going to take actually maybe about just the same amount of time, if not longer, because it's doing a little more work on the back end. So it did 7 seconds. When you're running the bigger loads, anytime you run a Spark job, there is upkeep to basically distributing that job to everything. So Spark runs more efficiently with larger data sets. So if I were to have pulled in a few gigs to terabytes of data in here, you would notice a drastic difference between the UDF and the Pandas UDF. So one of the other key takeaways, if you're writing in Python, make sure to use Pandas UDFs if you have to do a UDF, which is a user-defined function for those who don't know. If you're in Scala and you're writing a UDF, have at it, because a Scala UDFs are in its native language and will be vectorized anyways. So what we're going to do now is, because I'm with the Databricks Delta, I want to just kind of show off how you can easily cache data back into Databricks. Delta hates periods, spaces with a passion. So we're renaming columns here. We're basically just kind of going with renamed column this to rename it. And if you want to be able to type multi-lined in Python, you have to do the / / one slashes, slash you never use above enter. Run that will then rename everything. We can see the schemas. Because this is just doing a transformation. We're not actually running an action yet. So it's running next instantly and just kind of letting you know, hey, what you typed was correct. And then for Delta, if you're on Databricks, you can use Delta, which is essentially a file storage behind the scenes where it'll take care of all of your partitioning and parqueting. So it'll store dynamically parquet files spread apart in whatever location you tell it to on your Databricks cluster. So we're just setting up a location here where it's like Delta Pokemon. And then the format that we're writing out is Delta. So when you're writing out, before I said you could write out to as many any data source you want. Basically, before, if you're writing a parquet file out to your blob, you would just have this would be parquet, and you would just be pointing the location to your blob's phrases. And then once we do that, I'm just creating a new Spark table, SQL table from the Delta location, which is another example of how you could then interactively use batch with streaming. Because as you have that Delta Spark SQL table, you are able to just funnel all of your data from the streaming through Delta to your SQL table and interact with it like it's a batch data frame. So that way, as you're still streaming, you can still be running real-time queries against both streaming and your batch data, like it's batch, and you won't even realize that your data set's streaming. So I could you'd be able to, if you're doing the data engineering work, you would be able to give your data scientists real-time data without them actually realizing you're giving them real-time data. Every time they would run the data set, though, it would give them a different query response, and they would be really confused, though. So I would make sure they know that.
Can you open up the Spark jobs?
Yep. So this is running these. What we want to do, though, so we're seeing jobs 8 through 12. So let's go through the cluster.
I thought I saw something with Hive.
Yes, so it does like Hive partitioning and like Z ordering and Hive. Basically, it does like Hive partitioning setups with all the different data skippings.
Okay.
So as you can look at the jobs that way, or you can go into the clusters as well. So we're seeing this is jobs 8 through 12. So as long as we come in here and look at jobs 8 through 12, we can pull the data and look at it. So here is the details for what just happened. I'm not a Mac person. That's not what I wanted. So this one's doing a ton of, like, obviously a lot of different things. It's staging the data, it's doing some skips, and then it's just kind of serializing, deserializing, mapping the partitions out, and then actually executing on all those different plans through the stages. That's why you saw like the Hive load comes up, is it's doing all those different Hive map partitions. Different tab. So if your queries are running slow, this is where you come to be able to fix them in Nose, because you'll follow the exact DAG of what's happening, and you'd be able to tell, like, oh, this wholesale code gen's going to some random inner join for loop. Why is that happening? And it would cause a really nasty, ugly DAG, and you would be able to then have to, like a normal SQL plan, you'd be sat there digging through or seeing what's going on. When you're doing that, you just want to recognize the patterns initially. So like these are literally 3 of the same in a row. So the pattern is like quite obvious, but as it gets larger, you can have like unlimited amounts of these. And then once we create the table again, so we're back to the data frame, I ran just a count just to show that it actually loaded into Delta and then we're pulling from Delta. So we're at 9,600. And to end it, I'm just going to dump everything to a database by running a different database notebook, which I showed the example code earlier in the PowerPoints. It has all my passwords in it because I did not feel like creating a key vault. If you're ever using keys in Databricks, create a key vault, do the secrets, like especially if you're in production, you don't want that stuff leaking out. It's bad practice. Don't follow what I did in the demo. So that all just dumped over to the database, so we can just query it and see that's all there. It's a very cheap Azure database that spun up, hence how slow it was to pull such a little amount of data. So now we can just tell it's all there. You can output this in any ways you want. If you have like a Postgres partition set up, you can have it automatically do that. You can have it interact with your data warehouses, partitioning. You can get fun and creative. And one of the good things about when you're outputting and playing with the data, as you output anything, you can always just go to, let me make this big. Well, you can always do checkpointing. So if you look at where is it? The last option right before start, you're basically identifying a checkpoint location for your stream. So if your stream dies in the middle of doing anything, it knows exactly where to pick up from with the data. So you don't actually lose any data and you don't reload your data. So if you're in the middle of loading 500 gigs, it dies at gig 396, you restart it, it'll pick up right up at 396 and continue on its way. So you'll never duplicate your data and you'll never lose data. It's fault tolerant and it's wonderful. Use checkpoints if you're doing anything in production or dev test. Any kind of optimizations to remember, use your vectorized UDFs in Python, use your pandas UDF. Minimize data movements, I didn't really talk about that, but basically you want to force it to do the least amount of actions as possible so you can have the quickest compute. Anytime you're doing an action, it's causing Spark executors and jobs to spin up and run, which is more overhead that you have, which is ideally you want the least amount of those as possible to have the fastest, most efficient program as possible. Leverage your hardware. So the calculation I gave about how you can have your total size divided by the total size divided by size you're looking for the 200 megs. If you run that and use that as your amount of partitions, you will then have your cores at 100% usage for all of your partitions, allowing you to leverage everything well. So a lot of times when you see stuff running tasks twice, that means unless you did the math perfectly to ensure they ran twice, you would end up with 100% usage your first run and probably 70, 80% usage or less on your second run. So you're paying for all that compute and it's just sitting there. So make sure you do your partition counting and math correct. So that way you have full usage of your systems, which the hardware and sizing is all kind of together. And just because I really like koalas now, if you've ever used pandas in Python, it's a single node system, so you could deploy on Docker, run your pandas. They just released koalas a couple weeks ago. It is Spark version of pandas. You don't have to change anything at all. So if you had a data scientist working in pandas, testing everything, you could take their code, run it in Spark, and just change your import command from import pandas as PD to like import koalas as PD, and it would run and it would be distributed and run across all the executors and nodes. So I like to talk about it because a lot of people don't seem to know about it, but literally don't have to change anything going pandas to koalas, and you'll get the compute power of Spark. Are there any questions?
It's integrated with any source control, or how do you like?
Yeah, so you can, so if you're just doing Spark on anything like this is, where I'd be running on Kubernetes or Spark local, you can use any source control you would want, Git, Mercurial, DevOps. If you're using Databricks, which is right here, using like this stuff, they have a REST API you can use pretty much anywhere, but you're basically storing like ASCII encoded key images. So I usually would use the Azure DevOps or a Git-based one for that. I've never tried the Databricks inside of Mercurial. You could, but I would stick to GitHub, Bitbucket, or Azure DevOps. The REST API, if you're using Databricks to deploy everything, makes it phenomenal. And then the ways you can take care of that kind of stuff is you have a production notebook where 0 people have access to it, and you would just deploy everything to that notebook, and nobody would be able to see it besides like your super admin. And you would just set that up with your normal build release pipelines, and you would just use one like this Python class to do it all. Mm-hmm. I can actually show you how you. Since you mentioned that. So Databricks has a nice Git plugin inside of it where you can link it up right away. So in here, you can do, here, you see how it says Git not linked? You basically can, if you have your Git repo account, Azure DevOps or GitHub, you can link your Databricks up directly to that, and then use those classes, that Python class, to deploy everything. And Databricks naturally stores and tracks all your revision history like any wonderful IDE does. So if somebody ever comes in and gets your program, you can just revise it back. So we can look at some of my attempts of when I was actually figuring things out and getting it to work and realizing Delta actually hates periods and spaces. Because I've actually never encountered a data set that had a period or space in the schema name yet, until today. Yeah, that was a good question. Anything else? Feeling overwhelmed? Good? Bad?
Full.
I know, like, I went over a lot quickly. Basically, the takeaways: work on your partition sizing, use anything vectorized when possible to get to work. Microsoft has a Databricks course on LinkedIn, launched like I think a month ago. Microsoft's also, if you look at their data engineering certificate, I don't actually know how to get to their training material from there. So I go to the certificate, click the training button, like to help learn for the certificate, and they have an Azure Databricks course underneath that. They'll walk you through Spark and Databricks. What I would start off with the Spark Definitive Guide book. It's written by the creators of Spark. They'll walk you through everything you need to know about Spark. And then Databricks is just a platform to run your Spark. So the book will actually teach you how to get everything set up locally and run Spark shells if you want or anything like that. And if you want to fool around with streaming stuff, Kafka has a really nice beginner guide where you can basically turn your terminal into a Kafka server. So you can stream locally from your Spark to your Kafka server and basically play with everything on your local machine that way. You can also run PySpark and Jupyter too locally. So you don't have to do Databricks. It's just nice and requires zero effort to actually get going though.
So I have a quick question.
Yep.
You were talking about transformations earlier. What if you have, like you have a data set that that is constantly changing and you're trying to keep it accurate, up to date? How fast or how difficult would it be to implement?
Are you talking streaming or batch?
Batch.
Batch, you would just infer schemas and that would just take care of it all for you. Unless the only issue would ever come up is if one of those columns or something, the schema gets messed up with one of the ones you're doing a calculation on, but that would break pretty much any data process around.
Sure.
So,
yeah.
But if you were adding or removing columns that weren't really important to your data set that the calculations running, you can still carry all those with, so they still end up in your final data source. And you can set up your JDBC inserts in a manner to where you can basically, if the table in your database doesn't match the data frame coming in, you can tell it to be like, hey, blow this table away and make this new table with this new schema and start from scratch, which is a little risky, by the way. Don't advise it, but you can do it.
Mhm.
kind of fun to play with.
Would it have a solution for streaming?
No, stream.
No, yeah.
You change schemas. If you change schemas in any streaming environment right now, it's a headache. Like if you did in like Azure Stream Analytics or I don't know what other streaming services there are, but basically if you did in Spark or that, you would be having a bad problem then. Like when you're streaming your IoT devices in, if your schemas start changing on those, somewhere in your business process for your project, somebody dropped the ball and did not let you know and do a release correctly.
Well, if you had different types of IoT devices that had different data sending.
You would have different IoT streams then. They wouldn't all be on the same stream.
Okay.
So that would all be
Yeah.
individual like streams coming in. And usually if you're doing IoT stuff, you always route it through Event Hubs or Kafka or Rabbit or Service Bus. Event Hubs, Kafka are like the bigger ones that are more resilient and can handle unlimited streaming events. Kafka, Service Bus is a little smaller, but still work wonderfully. Service Bus and Event Hubs, for those who don't know, are the Azure versions. Kafka and MQ Rabbit are the open source versions. Kafka being the equivalent of Event Hub, Service Bus being the equivalent of MQ Rabbit. Yep.
Yeah, Spark is actually a lot faster than Hadoop, but can we use Spark as an API, for example, for a web application or something? Can we use Spark as a backend?
Yeah. So like if you want to, so like in my example, I was pulling in CSV. If you wanted to use Parquet to do like, oh yeah, let me go to the PowerPoint version of it because I don't show that code. So right here, and let me make big because it's tiny. So you see how it says, where does it say CSV? It doesn't say CSV. Yeah. Basically, it's telling you to just be separated by the comma with the .csv. You could have CSVs coming in as pipe delimiteds. I've encountered people who do it. It's really weird. I don't know why. So I always include the separations. You basically would just change the word CSV to Parquet and would read your Parquet and remove the separation. And then you can always, you would output the same way. So you would output to your blob. And instead of this is being set for a JDBC. Instead of saying JDBC, you basically be like Parquet and then send it to a blob or S3 storage or wherever you want to go. So until recently with Databricks Delta, anytime you were looking for quick optimizations on your data loads, you would write out to Parquet really quickly so you could get your partition set up and then read those partitions back in. Delta allows you to do it natively inside the Databricks, so you don't actually have to control a different data source. But Spark was born, always use Parquet ideally. But it can read anything and output anything. Any other questions, comments, concerns? Everybody like the pizza?
That's really good.
A lot of information to digest.
Yeah.
Yeah.
If people are interested, I'm definitely willing to do more of these where I actually pick one topic at a time and cover that more in depth rather than basically taking a waterfall to everybody and be like, enjoy.
The fire hose.
If you could do one for the data movement stuff.
Yeah.
That would be.
Yeah, I can do one for all aspects of Spark, anywhere from ingesting to outputting, using streaming, not streaming, machine learning stuff.
Cool.
Well, thanks everybody for coming.
Thank you.
Appreciate it.
Take a train. 7:03. Oh, I got it.
Bye, everybody who called in.
I'm sorry.
Stickers are cool.
I like. I know, it's like.
Yeah.